John Dalton's resurrection of the idea of atoms brought about a flurry of activity in which chemists and physicists tried to determine both the chemical properties and the size of the many different atoms that exist. Then a debate emerged in the scientific community, whether to organize these so-called elements by size or by chemical properties. The debate was resolved by a Russian scientist named Dmitry Mendeleev, who realized that these two ideas were not mutually exclusive. So he compiled a master list of all of the elements that other people had studied, and he started arranging them both in terms of increasing size, while also keeping track of their special chemical properties. This table eventually came to look more like this: the periodic table of the elements. Scientists decided to bring back that word element from Aristotle's day to represent distinct types of chemicals, such as hydrogen, helium, lithium, etc. Each element has a unique type of atom, and there are 6 elements that we will encounter over and over again this year, as they are the most common in organisms: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The periodic table is particularly clever because it organizes these elements by both size and chemical properties. How so? Atoms are ranked by size using their atomic number. So you can see the smallest element, which is hydrogen, has an atomic number of 1 and is listed here, and then up to helium, and then down to the next row, lithium, beryllium, and so on, increasing by size as you go down each row and across it. Each row as you go across is called a period. For example, hydrogen is the first element in the first period, or period 1, and then lithium and beryllium are in period 2. This is sodium and magnesium are in period 3, and so on. So each row is a period in the periodic table, and as you move down from period to period, you'll notice those atomic numbers getting larger and larger. So again, the periodic table arranges elements by size. But not just by size, also by chemical property. For example, in the groups or families, that's the descending columns, so there's family or group 1, here's family or group 2, family 3, and so on. Each of these share similar chemical properties. For example, the elements that are over here on the left all have very violent reactions with water. There was a chemistry major at my college who wanted to play a prank, and he did so by taking potassium, which is one of these elements in this column, and chucking it inside a toilet in his fraternity. Now, he could have chosen sodium or lithium for this prank, because all of them would have reacted with water very violently. Needless to say, the toilet exploded. However, not all the elements have explosive reactions. On the other end of the periodic table, in this period called the noble gases, which is all the way on the end, these elements don't react at all. A fancy way that chemists say that is that they are inert, meaning non-reactive. So you have all of these inert elements in one family or group, and you have very other reactive chemicals in other families and groups. In other words, each group and family has similar chemical properties. So the periodic table does a good job of combining both of those sorting principles, size and chemical properties. But what is it exactly that makes a carbon atom different from a nitrogen atom? For that, we need to understand what atoms themselves are made of. In order to understand how the world works normally, scientists often look at the world when it's working abnormally and compare that to normal. That's exactly what Becquerel and the Curies did in the 1800s to better understand the internal structure of an atom. To help you better understand the experiment, I'm going to give you a modern understanding of what an atom looks like. Then we'll go back and try to understand things from Becquerel and the Curies' perspective. Atoms, like this helium atom that I just drew, I'll put He, its symbol, in the corner, are made up of 3 subatomic particles: protons, neutrons, and electrons. The protons and the neutrons are held in the center of the atom in an area known as the nucleus. But Becquerel and the Curies had found some very strange atoms. They were called radioactive isotopes. These guys had no idea what an atom looked like or what a radioactive isotope looked like, but modern scientists have since discovered that radioactive isotopes are a version of an element with an abnormal number of neutrons in its nucleus. Now, Becquerel didn't know this was true of the uranium salts he was experimenting with one day. He just got to the end of a long lab day and decided, hey, you know what? I've got these uranium salts, but I don't have time to experiment with them. I'm going to go put them in a drawer. And by coincidence, he put them into a drawer on top of a piece of photography paper. When he took the photography paper out several months later, he noticed that without even being exposed to the light, the photography paper had developed a stain on it that was the exact size and shape of the bag of uranium salts. He and many other scientists found this interesting and wondered what secrets about atoms these strange salts could reveal. The Curies, especially Marie Curie, got right to work on this. Luckily, Marie was recognized for her excellent work and was made the first female professor at Université de la Sorbonne in Paris. Compare that with poor Madame Lavoisier, who had to publish all of her work under her husband's name, and so he got the credit even though she was the mastermind. Luckily, things are constantly getting better for women scientists. But anyway, what did the Curies discover about radioactive isotopes? They took some of Becquerel's uranium salts, and leaving it out, noticed that every so often, a substance would come out of the uranium salts during something called a decay event. Uranium is such a huge atom, with an atomic number of 92, that its nucleus is so big as to be unstable. That means from time to time it will fall apart or decay, and a small particle will come zooming out of that nucleus. The particle was named an alpha particle, and it could be deflected by the positive end of a magnet, so they knew that these particles had a positive charge. By the way, future researchers figured out that this alpha particle was positively charged because it contained 2 protons in it, as well as 2 neutrons. But when the Becquerels turned back to the uranium salts, they found that the salts were no longer uranium. They had become an entirely different element called thorium, which has an atomic number of 90 instead of 92. The Curies concluded 2 things from their experiment. One was that all atoms have smaller particles within them, and the other is that that number of particles that they have determines whether they are one element or another. From there, other researchers, such as the Englishman J.J. Thomson, went to study what exactly are these particles that distinguish one element from another. In 1897, Thomson discovered one of these so-called subatomic particles, now known as the electron. He demonstrated its existence using one of these cathode ray tubes. A cathode ray tube is evacuated. That means the inside of it is a vacuum, so there's no air. And he would run wires to either end, one of which would be positively charged and the other of which would be negatively charged. Now, charged metals give off electricity, and he could get the electricity to go shooting across the middle of his cathode ray tube from one end to the other. Now, this beam, or constant spark of electricity that was running from one node to the next, had some special properties which he discovered when he started to play with some magnets. So, for example, if you took a magnet and you put it in this orientation, with the positive end pointing towards the beam, then the beam would start to deflect like this. Ooh, it would start coming down this way before it would go shooting back up to the node. In contrast, if you put the negative end of the magnet towards the beam would have the opposite behavior. It would deflect to the other end of the tube. This really puzzled Thomson, and he was worried that some confounding variable had slipped into his experiment, so he went back in and built a whole bunch more cathode ray tubes, and each time he would use a different metal for the node, but always the same thing. The particles would always deflect away from the negative end of a magnet towards the positive end of a magnet, and they would always deflect the exact same amount. Now, in electromagnetism, opposite charges attract, and like charges repel. This left J.J. Thomson with only one conclusion. The beam must have a negative charge, because only a negative charge would go zooming towards this positively charged end of a magnet, and would go zooming away from the negatively charged of a magnet. And that in turn meant that, since any metal he used for his cathode ray tube would always deflect the same amount, that means that any metal And probably any substance, period, had to have a negatively charged particle inside of it. He called this particle the electron, negatively charged. And knowing now that all atoms had electrons in them, he sat back to think about what those atoms must look like. And he imagined that they resembled a bowl of plum pudding, and so he called his model of the atom the plum pudding model. So he pictured that atoms were spherical, like plum pudding, and that floating around in them were small electrons that were negatively charged, kind of like the plums inside the pudding. He then reasoned that the rest of the plum pudding must have a slight positive charge. After all, most substances are not charged. Like if I put a magnet against your face, the magnet wouldn't stick to your face. So that means that in addition to having the negatively charged electrons, your face must also have some positive charge. So J.J. Thomson assumed that the little electrons were floating around in a sea of positive charge that made up the rest of the atom. The positive would cancel out the negative, and overall, most substances would be made of atoms that are neutral, or without charge. Ernest Rutherford hears about Thomson's idea and says, interesting hypothesis. I'll test for this sea of positive charge. Ernest Rutherford chose the perfect materials for his experiment. First of all, he used alpha particles, the large positively charged particles that the Curies discovered were coming off of uranium. He would use them by placing uranium inside a lead block, which would trap most of the alpha particles, and only let them out of a single hole. Right in its trajectory, he placed a piece of gold foil. Gold is very malleable, so Rutherford was able to hammer it until it was extremely thin. So he said to himself, if J.J. Thomson is right, then that gold foil is really just a very light, thin sea of positive charge. And a sea of positive charge shouldn't be able to stop a cannonball alpha particle from zooming right through it and to the other side. And indeed, most of the time he was correct. Most alpha particles were able to pass right through. However, on rare occasions, some of the alpha particles actually bounced off the foil and got sent in a new direction, hitting the photography paper in different spots. When Rutherford got this result, he couldn't believe his eyes. Here's what he wrote in his journal. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, that's a bullet, at a piece of tissue paper and it came back and hit you. This made him think very differently about the gold foil. It couldn't just be a sea of positive charge, because if it were, all the particles would be able to pass right through. Again, here's a quotation from his journal. On consideration, I realized that this scattering backwards must be the result of a single collision, and when I made calculations, I saw it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute, massive center carrying a charge. In other words, he realized that at some parts in the foil, there had to be tiny positive charges that were way bigger than the incoming alpha particles. That means that when an alpha particle, which also has a positive charge, bumps into this big positive charge, it would then go bouncing off and ricocheting away just the way he saw, since positive charges don't like to hang out with each other. Meanwhile, most of the rest of the alpha particles went zooming by and didn't make contact with the positive charge and were able to go straight through the gold foil. Other researchers built on Ernest Rutherford's experiment until they developed what is known as the Bohr model of the atom. This is an atom that was used in the early 1900s and that we'll use in our class. In the Bohr model of the atom, there is a nucleus found in the center that contains both the protons, which are positively charged, and the neutrons. That's what Ernest Rutherford discovered. And then around the outside are those electrons that J.J. Thomson discovered, moving in shells or clouds. This means that most of the atom, surprisingly, is empty space. To Rutherford, this made sense because that's how the alpha particles could get through that gold foil that seemed solid to his eye. But to most of us, it's pretty hard to imagine. And when I say mostly empty space, I mean it. If we were to take an atom and increase it to the size of Gillette Stadium, The nucleus would be about the size of the ball sitting at the midfield. And the electrons would be the size of a fly out in the parking lot, flying around the outside of the stadium. And everything in between is empty space. So when Democritus thought of the idea of atoms in 400 BCE, he had no idea where researchers in the 1900s would get us. I bet that even you are having trouble believing that the chair you're sitting on right now is mostly empty space. But that is the beauty of science, an endeavor in which one experiment builds upon another, which builds upon another, and we continuously uncover more and more miracles of this universe.